It's interesting, yeah, because this you could have a computer which is everything set at 0, but this will be the possibility of an information system because these can then go on and off, and it can be copied. There was one point I didn't quite understand when I read it, which was if the thing's kind of full, then it isn't hasn't got information, or are you saying that it isn't an information system anymore because it can't change? It may contain. I mean, there's kind of difference between if something contains info. I would say when my hard disk is full, it's still got information even though I can't change it anymore. Or are you saying, well, no, I'm defining an information system. It's now no longer capable of being an information system, even though it might contain my photos and stuff and.
Yes, I guess you can still have information in a system, but temporarily this system is, not able to be rewritten. But in a way, when you have a memory that's full, imagine you suddenly could change the laws of physics in a way that you cannot extract that information anymore. So, for example, copying isn't possible. In that case, although you could think that it makes sense to describe the state in which the object is in and so on, it loses this nice property of being interchangeable with other objects that can flip and then can have this copyability property. So it somehow has lost one of the nice properties of objects that we expect are able to process and contain information. So I guess whenever we have a memory that's full, we're always thinking that there is one way of transferring whatever that is in there into some other system through, for example, a copy operation, which would then allow us to erase this memory and then reset it to whatever initial state it had. But if it's somehow for reasons that have to do with the laws of physics, fundamentally stuck on this particular state, and it couldn't be flipped back into not containing anything or the blank state, then it wouldn't be a good information medium anymore, because it's not interchangeable anymore with all the other kind of bits that exist in the universe. So I think that's the kind of idea.
Yeah, and then what I was intrigued by was you then sort of push this and sort of focus in on particular information systems, namely ones which are exploiting quantum physics, which of course are incredibly interesting at the moment as people are actually trying to make quantum computers. So understanding the kind of the idea of quantum information is becoming not just an esoteric pursuit, and so you add a couple more of these counterfactuals to actually define a sort of quantum information system. So could you a little expand on how you do that?
Yes, I think this is a kind of thing that emerged out of this field of quantum information. So it's quite nice that we understood quantum theory better by trying to understand the information theory that is possible with quantum systems. And again, this is because, as I said before, in regard to bits, when you concentrate on the information theoretic properties of systems, you're getting rid of all the details that are unnecessary. And so you don't worry anymore whether you've got an electron or a proton or, I don't know, a photon. You can call all of them a qubit, which is this unit of quantum information that has some additional properties to a bit. And these are, again, counterfactuals. So a qubit can work as a bit. So it has this copyability and this possibility of having, a number of different states that can be flipped into one another. But it has more. And the more part of this is connected to this property that kind of we've heard about a lot when we talk about quantum theory. I think the first thing that comes to mind is this Heisenberg uncertainty principle. And usually it's introduced as the start of why we lose kind of our grip on understanding physical reality somehow, because it says something that physicists initially didn't like quite. So it says that objects like electrons have different properties. These properties are like velocity, position, energy, etc. But some of these properties cannot be measured to the same arbitrarily high accuracy by the same machine. And what does that mean? It just means that when we're looking at the electron, while classically we can, in principle, determine with the measurement both velocity and position arbitrarily well, with the electron we can't. So, we can either measure really well position and then we lose a grip on velocity, or vice versa. Now, this is again about impossibilities, because this principle says that a machine is impossible, and this is a perfect measurer of both position and velocity for the electron. And now, abstracting away all of these details about the electron, a qubit in general is an object that has, let's say, at least two different ways of containing a bit. So velocity and position, for example. But if you try to use both these ways to jointly contain information, you will fail, because you can't specify with very, very high accuracy both these bits. So you either prepare the velocity bit to great accuracy, but then you can't use the position type bit, or you prepare the position type bit and you can't prepare the velocity type bit. So in a way, a qubit is more interesting because it has multiple ways of encoding a bit, but all of these ways can't be used jointly. And that's what the Heisenberg uncertainty principle tells us. And it's very interesting that this particular thing allows you then to have more in terms of information processing abilities. And that's kind of a counterintuitive, very cool thing that quantum information pioneers realized.
Well, what I thought was very striking was then your statement that, hey, actually, quantum physics might not actually be a theory which survives. It might change and be something different. But what's beautiful about what you've done is that, but this definition of using counterfactuals can be made independent of quantum physics. Another theory will have will fit in a different ways. So for me, this really showed the kind of power of your vision, which was to kind of change the order we do things in a way. You want to make the counterfactuals not a consequence of everything that we're seeing, but almost like the principles. But so let's identify the fundamental principles, and almost then, you might have a theory which then gives you an example of this, or maybe things are implied by the counterfactuals. I mean, that seemed to be the real challenge. You want to make these the beginnings, it's reductionism, but to counterfactuals, not to particles and trajectories.
Yes, I love this way of putting it that you just came up with. It's I think this is what somehow fascinated both David and me when we started thinking about this particular thing about information. It was tantalizing, the idea that you could find some kind of hidden symmetry in quantum theory through this idea of following the counterfactuals that underpin information in that theory. And then use that as a sort of springboard. So these principles about counterfactuals as a springboard to then guess the successor of quantum theory, or maybe help us finding exactly this theory that won't just be the successor of quantum theory, but will merge it with general relativity, and so help those people who are studying quantum gravity and stuff like that.
Yes, you talk about it.
I know that you like symmetry, and I think this is a very nice way of explaining how powerful finding symmetries is.
Could you expand a little bit on, because you wrote in the book sort of tantalizing hint at the use of counterfactuals to kind of explore this idea of quantum gravity, that gravity might need to be quantum. And again, it seems to hint at the idea, well, we might not necessarily need to know what the two theories will be that will finally merge, but using the counterfactuals, we can start to explore it even before we know what the answer might be. Could you give us a little hint about what that means and how it's being used?
Yes, I think so. This is a train of thought that started with physicists already, in the past, in a way of so people were trying when they realized that quantum theory and general relativity were two very different theories, and they somehow disagreed about the universe, because general relativity is very different from Newtonian physics, but it's classical, so it does not have this Heisenberg uncertainty business. It doesn't have this additional limitation on what you can measure and so on. So everything is just like in good old Newtonian physics. So there's a tension. And so back then, people like Feynman, Wheeler, and DeWitt and other physicists tried to come up with ways of still making predictions about what happens when gravity, which is described by general relativity, gets to interact with something that's quantum, like a mass. And I think this problem is at the heart of quantum gravity, because on the one hand, general relativity says that gravitation is universal, so anything that has an energy has to interact somehow with gravity. So there's no way of shying away from gravity. But at the same time, quantum theory says that things that have energy can also, and mass, can also manifest these quantum effects where Heisenberg's uncertainty becomes important. And so, does it mean that when we have a mass or a kind of quantum system that displays these quantum effects, does it mean that it will infect gravity with this quantumness? Or does it mean that does this mean that gravity will somehow make this mass classical, back into a classical system, and let it forget about Heisenberg's uncertainty? I think that's the kind of question. And back then, I think already they tried to use principles, general principles, to make predictions about this situation where a quantum system interacts with gravity, because the dynamical laws we had were not so well developed at the time. So, there were some attempts to quantum gravity back then, but they were not fully developed. And even to this day, I think even though there are nice proposals for quantum gravity that are really fully developed and nicely mathematically expressed, there is still this problem that because we haven't had really experimental confirmation of which one is right, when we have a situation of that kind, we're still not sure, which dynamical law we should use. And so these principles and counterfactuals come in very powerfully here, because they still apply. These features of things being possible or impossible that come from the deepest symmetries of some of these dynamical laws that might be important in this particular regime are still applicable in this context. And so they allow you to make predictions still, even though you don't know particularly which dynamical law you're using. And so that's how I think some kind of worked with Vlatko Vedra, who's a physicist here in Oxford. We came up with an idea to, as you said earlier, to make a test that allows you to, just based on these counterfactual general statements, allows you to check if an unknown mystery system has or doesn't have quantum features. And this is very useful because even though this is like a thought experiment, so it's very abstract, but in principle is realizable, it's useful because it allows us to think of ways of probing gravity, or in fact any system that's a bit mysterious, about which we don't know exactly the details of its dynamical laws, in such a way that we can check whether it has quantumness in it or not. So it's like a sort of witness of quantumness, which doesn't rely on the quantum laws of motion. And that's the kind of nice thing, and which comes directly from the generality of counterfactuals. So I think that, yeah, that's a very interesting recent development, which was very exciting to us somehow because there's a connection with experimental consequences.